Okay, so we're going to talk about lesson 12-3. If I could get this to work. And we're basically going to talk about distributions of data. Okay, so we're going to talk about how data is distributed. Based on the distribution, we're going to determine whether the mean is a better representative of the average or median. Okay, so we're just going to call it distributions of data. And today's date is, oops, not June yet, the last day of May. Okay, so let me talk about what distribution is. Let me talk about histograms, and then we'll talk about the distributions and how it relates back to Box and Whiskers Plot. So what is a distribution? So distribution shows the observed or theoretical frequency, so what you see, or theoretical. Now when you talk about theoretical, it's things that you can calculate using formulas and other ideas from math. So there's a lot of theory in math. So based on a theory, I can come up with an answer. Okay, so it's that sort of idea. So it shows the observed or theoretical frequency. So how often something shows up of each possible data value. So the distribution will indicate whether the mean or the median better represents the data. So what some people do is they take data and they organize it using a chart, and from that chart they create what they call a histogram, and based on what they see from that histogram, they'll make a determination. And then also the second would be to do a box and whiskers plot or box plot, and based on the distribution they will make a determination whether the mean or the median would be the best choice. So let me talk about a histogram. I'm not exactly sure how that name came about. But a histogram, it's a type of bar graph where the bars touch, so that's different. And data flows from one bar to the next. And data is grouped in equal intervals. So basically you're going to look at your set of data and you're going to look at how many numbers do I have from 0 to 9, 10 to 19, 20 to 29, 30 to 39, 40 to 49, and so on and so forth, or whatever your data set holds, okay? So basically, let's do one with just doing a histogram. So let's have a set of data. And this one deals with, it doesn't give me a parameter behind where it is. So I'm just going to list, and histograms tend to have a ton of data. Another tool that we use when we have a ton of data is a stem and leaf plot. And that helps us quickly organize our data using the stem, which is the tens value, and the leaf, which is the ones value. And we very quickly can write things and then reorganize it into numerical order. So maybe what I'll do is show you both of those, and then we'll get to the histogram. So you know what, I'm going to go to the next screen. I'm not going to start it here, so let me take this off, and we'll go to the next screen. Do you guys remember stem and leaf plots?
Yes.
Okay. So we have, we're going to ask you to make a histogram. Of the data. So I'm going to give you a whole bunch of stuff. So you got to make sure you get everything written in. 25, 22, 31, 35, sorry, 25, 26, 35, 18, 39, 22, 32, 34, 26, 42, 23, 40, 36, 18, 30, 26, 30, 37, 23, 19, 33, 24, 29, 39, 21, 43, 25, 34, 24, 26, 30, 21, 22. So again, when we use a histogram, when we use a stem and leaf plot, is when we got a ton of data. So what I notice is there's not one single digit number. So when I do a stem and leaf plot, I'm going to start with tens, and I'm going to do 20s, and then I'm going to do 30s, and I don't skip any stems. And it looks like we even go to the 40s. Do we have anything in the 50s? No, it looks like this. So what I start doing is I go through each of the numbers that I see, and I list its leaf, okay? So 25 has a leaf of 5. I put it with the 2. 22 has a leaf of 2, and I put it with the 2. 31 has a leaf of 1. 25 has a leaf of 5. 26 has a leaf of 6. 35 has a leaf of 5. 18 has a leaf of 8. 39 has a leaf of 9. I mean leaf, yeah, leaf. 22 has a leaf of 2. 32 has a leaf of 2. 34 has a leaf of 4. 26 has a leaf of 6. 42 has a leaf of 2. 23 has a leaf of 3. 40 has a leaf of 0. 36 has a leaf of 6. 18 has a leaf of 8. 30 has a leaf of 0. 26 has a leaf of 6. 30 has a leaf of 0. 37 has a leaf of 0. 23 has a leaf of 3. I said 0, but I wrote 7. Sometimes my brain just looks at other things. 19, oops, sorry, go back. 19 has a leaf of 9. 33 has a leaf of 3. 24 has a leaf of 4. 29 has a leaf of 9. 39 has a leaf of 9. 21 has a leaf of 1. 43 has a leaf of 3. 25 has a leaf of 5. 34 has a leaf of 4. 24 has a leaf of 4. 26 has a leaf of 6. 30 has a leaf of 0. 21 has a leaf of 1. And 22 has a leaf of 2. So I write it down like that, and now I'm going to do the 7-leaf plot a second time, but what I'm going to do is organize my leaves into numerical order from least to greatest. So this is probably the fastest way to organize a large group of data. So my 10s are super simple to put the leaves in order because they happen to be in order. So I had an 18, an 18, and a 19. Okay? Now, let's see what we got here. We've got 2 1s under the 20s. We've got 1, 2, 3 2s. And one of the things you want to do as you're writing your leaves is that you line them up underneath the leaves from above. So the first leaf matches first leaf, third leaf, third leaf, and so on. So let's see, do I have any 3s? I see 1, 2 of them. Okay, 4s. 1, 2 of them. 5s. 1, 2, 3 of them. 1, oops, sorry, not you. You. 6s. 1, 2, 3, 4 of them. And I have 1, 9. So what I do is I count how many I had originally. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Now, remember those numbers aren't 1, 1, 2, 2, 2, 3, 3. They are 21, 21, 22, 22, 22, 23, and so on and so forth. Now I'm going to go with the 3s. Let's see, I have 3 0s. I have 1 1. I have a 2. I have a 3. I have 1, 2 4s. I have a 5. I have 1 6, 1 7, and 2 9s. So I double check and I count my leaves. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then I check what I just did. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. Yeah, I kind of smushed 2 numbers. Wasn't really pretty what I had there. And then the last, for the 40s, is pretty easy. We have a 0, a 2, and a 3. Now, 7 leaves plots, what your teacher taught you this before may not have explained to you that you can actually figure out the median pretty simply from a stem and leaf plot. You can find a mode very easily in a stem and leaf plot, and you can actually, there's kind of a quote-unquote faster way of doing mean in a stem and leaf plot than what we had to do with mean, which was just add, divide by how many numbers there were, okay? So I'm not going to go through the mean at this point. What I'm going to, which you would need to do, and I would recommend you using a calculator, and maybe I'll just show you that. But what you do to figure out your median is to count the leaves all together. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. So I have 36 numbers. So what would be considered the halfway point of 36? 18. So what I'm going to do is figure out where the 18 falls. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I have an even set of data, and my 18th number falls between two numbers, or when I cut it in half. So my median is going to be between 26 and 26. So what's the median? 26. So all I did is it was a fast way of counting where the middle was. And it's a fast way of putting numbers in order from least to greatest when I have a large set of data, okay? Now, let me show you how I would do I won't calculate it out, but you may need to do this on your homework. What if you were asked to figure out mean? Let me show you how I would do that with this data. So what I do is I have 3 numbers in the tens plus the leaf digits. So there's an 8 plus an 8 plus a 9. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 numbers in the 20s. And then I would add the numbers. So here's where having them in order from least to greatest speeds up the process. I have 2 numbers that are worth 1. I have 3 numbers that are 2s. I have 2 numbers that are 3s. I have 2 numbers that are 4s. I have 3 numbers that are 5s. I have 4 numbers that are 6s, and I have 1 number that's in the 9s. Now, already I'm hearing whining and going, oh my gosh, this is so hard, this is so hard. No. This is reality, okay? So let's see. In the leaves for the 30s, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I have 13 numbers in the 30s. I don't have to add the zeros. So I have a 1, I have a 2, I have a 3, I have 2 4s, I have a 5, I have a 6, I have a 7, and I have 2 9s. And then I have 3 numbers in the 40s, and the leaves are 2 plus 3. So that's how I would figure out the mean. I would take that, and then I would divide by 36, because that's how many numbers I had altogether. Actually, the numbers are simple enough that you would not need to use a calculator, but knowing this group and their level of trying to do math without aid, calculator probably would come in to play. Okay? So again, stem and leaf plots, super helpful when you have large amounts of data. Yes?
So if on homework, can we use a calculator?
Whine. Do whatever you need to do. Do whatever you need to do to get to the answer. Now, I want to make my histogram. And the histogram is a lot simpler. In the histogram, what I do is I count how many numbers in the tens I have. So I've got a total of 3 numbers, and all I'm counting are my leaves. In my stem, let's say I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 numbers that are in the 20s. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 numbers in the 30s. And I have 3 numbers in the 40s. So when I do a histogram, I'm going to go to the next page so you can see this. I'm going to create a bar graph. And my numbers in my bar graph are going to be from 10 to 20 to 30 to 40 to 50. So you can start with the zeros. So a histogram only looks like this. Actually, you know what? Let me kick up some graph paper. And let's see. My largest number was 17, right? So we have 18, 16, 14, 12, 10, 8, 6, 4, 2, and then this would be the 0 point. So this would be unnecessary. And this would be unnecessary. So 10, 20, 30, 40, 50. Oops, started writing it in words, how silly. Hold on a second. So this is 2, 4, 6, 8, 10, 12, 14, 16, 18. So the bottom is your intervals, and the y-axis is the frequency of those intervals. So somebody remind me, how many numbers in the tens do we have? 3. So my bar, oops, for the tens goes up to 3. And then it went up to 17, right, for the 20s? Is that right? So the bars touch each other. Okay, and what was it? Was it 13 for the 30s? 13? And do we just have 3 for the 40s again?
It's all kind of coming back.
Okay. So that's what the distribution of the data would be for this particular one. So how we interpret this is based on what the bars look like. So it breaks down into 3 possible distributions, okay? So let me talk about the 3 distributions. And these are generic. So distribution 1 would be considered negatively skewed data or distribution. So a negatively skewed distribution, you would have something that looks like this. If I try to kind of draw around my information, so I kind of just go through, that's what your data would look like, okay? That's negatively skewed, meaning there was a tail at the negative side, the left side. So there would be a tail on the left, okay? So it's basically saying the majority of the data is to the left of this diagram. Okay, so then we have another possibility, which would be symmetric distribution. So in this particular case, you're going to see something that looks a little bit more like this. Now, it may not be perfectly like this, but very similar, where there's a balance and there's a kind of a hump in the middle. And again, if I drew around it, it looks what we call a bell-shaped curve, okay? So we would say there's no tail, and data is evenly distributed. Okay, so before I have to listen to one more sigh, What you've learned in statistics before was mechanical. Now you're understanding why we learn it, okay? That's the whole point to things. Michael,
For the graph we did, what was it for?
what was your question again?
For the graph that we made, would it use symmetric distribution?
No, I would say it's more of the next one we're going to talk about, okay? And that would be a positively skewed data. So this one's going to look more like this, where we start off with something kind of small, and then it shoots up, which is what you're seeing here. And then it kind of comes down. And so if I drew around it, it would look like this. So if you notice, you have a tail on the right. And we would say that the majority of the data are on I did this backwards, sorry. This is where the majority of the data is on the left. This on the negatively skewed. This is on the right. So we have this peak up at the top on the right, where it gets heavier on the right. So this, again, this one's hard to tell because we have such few bars here. But we would say, again, ours would be of the pictures. If I drew a picture for ours, it looks more to the right, positively skewed with a tail on the right than it did on the left, okay? So, of these three, two of them don't look good for medians. One of them only looks good for mean. Which one do you think mean would be the best one?
Symmetric.
Yeah. So this is the one that you would use a mean on. And these you would use medians. And again, the situations would be, let's say on a negatively skewed distribution would be like a pay scale that includes the CEO's pay, which would make the mean look larger than it really is. And can't really think of one off the top of my head for the other situation. And the positively skewed, where smaller is better. All right, so let's now take this same idea and let's say, what would a box and whiskers plot look like? So for box and whiskers, if we had the negatively skewed, if you notice that we've got a long whisker on the left and a short one on the right, we find that the median is closer to the short whisker. That's considered negatively skewed. So, left whisker longer, than the right. And the median, remember that's the line in the middle of the box, is closer to the shorter whisker. So just to give you a comparison up here, I'll just put in what we're seeing for the data. So remember, from here to here, so from the left whisker to the median, that's 50% of the data. And, oops, I went too far on this one. And then from the median to the right whisker, that represents 50% of the data. So if we have more data to the left, that's negatively skewed. Okay? Symmetric. So on the symmetric, we would have something more like this. Now let's bounce it out. Okay, so again, if I give kind of a qualifier up here, from the left whisker to the median, that's 50% of your data. And from the median to the right whisker, that's 50% of your data. So if you can see, things are pretty evenly displayed out. So key things here is the whiskers are the same length. And then the median is in the center of the data. Okay. And then for positively skewed, it's going to be the opposite to what we saw with negatively skewed. So again, if I draw, I'll do it underneath this time since I scrunched myself out of room here. So from here to here is 50% of the data, and from the median to the right whisker is also 50%. You can see that you have more data, you have more values to the right of the median, so that would be considered positively skewed. Okay, so again, this also can help you understand what would be a better, oh, let me write down the ideas, is that the left whisker is shorter than the right, and the median is closer to the shorter whisker. Okay. So again, the idea is, what would be a better way of looking at the data? Basically, again, this would be mean. Median would be a better representation of the data when you have this or this. Now what I'm going to do is go back to the distributions we showed on the page before. And I'm going to kind of play where the median would fall and where the mean would fall. So the easiest one is here. This value is going to be the mean. And, believe it or not, it should be also the median. When we have a perfect distribution, okay? When we have the negatively skewed data, the mean is going to get pulled to the right. The median is going to be more what's in the center. On the positively skewed data, oh, did I do that wrong again? Yeah, I did. Sorry. Yeah, I did that wrong. I just rearranged my words. Let me change it. Sorry. The one to the left, that's going to be the mean. And the one to the right is going to be your median. And then on the other guy here, you're going to have the median is going to be closer here. But the mean is going to be to the right of that. Because the smaller numbers are going to pull it smaller. So when we talk about statistics, when we have a positively skewed data or distribution or negatively skewed distribution, then what you're going to be wanting to use is the box plot. Let me change this word to distribution. When you have symmetric distribution, that's where you're going to use mean and standard deviation. Standard deviation and mean don't make sense if I've got positively or negatively skewed. Okay, so it just kind of gives you what you should be doing. So basically the idea is take your data, make a histogram. From the histogram, because it's organizing your data in order from least to greatest, make a box plot. Okay, and I can use the data from the histogram to make a box plot pretty easily. I've already figured out what the median data is. I have 18 numbers, so between the 9th and 10th number would be the middle. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So that would make 23 the first quartile. And then I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's going to be your 34. That's going to be your third quartile. You have your least data and your greatest data. So the stem and leaf plot can help figure out all the things you need. So for me, organizing large sets of data, I start with a stem and leaf plot. From there, I can do a box plot, or I could do a histogram, and both of those will reveal whether you have a symmetrical set of data, a skewed left or skewed positively or skewed negatively, and then from there, it'll tell you what is your better calculations to be using. Should I be basing my information on median? Should I be basing my information on mean? Okay, Michael. It's the same thing as we did before, but I don't have to list out the numbers. I list out it's using the leaves because the leaves represent each number that's in the data. So if I find where my half is, then I need to find the middle of the first half. Well, I have 18 numbers, so half of 18 is 9. So between the 9th and 10th number, because it's an even set of data, is going to be my first quartile. Between the 9th and 10th number of the second half is also going to be a median, but this time of the third quartile. Okay? And then first and last is easy. Okay? Have fun with this.